Hi guys, really short video, I promise. Covalent bond strength, chapter 8. Oh, it's actually section 8. You'll have to correct that in your notes. Okay, so bond strength is how much energy it takes to break a bond. Here you see a chlorine-chlorine bond, and this is a Cl2, and if you break it apart and you get two Cl's, the Cl ion, so this is actually this, if we were going to write it like that, okay? The amount of energy it took to do that is its bond strength. And think about it, the more energy it takes, the stronger it is, right? When we talk about the strength of somebody, we talk about their ability to overcome something, right? So here's the bond enthalpy for Cl bond is 242 kilojoules per mole. And if you look over at this table right here, you can find chlorine bond somewhere on here, right here, 242 kilojoules per mole. You would get these bond strengths from a table, okay? And look what it says down here. The average bond enthalpies, they're average, they're not absolute, okay? Because think about it, you've got a carbon-hydrogen bond in several different types of molecules, and depending on what that molecule is, whether it's a carbon-hydrogen bonded like this, with 4 hydrogens all around the carbon, or it's this, where you've got 3 chlorines and 1 hydrogen, okay? The bond strength is going to be different because in this one, there's equal pull on all sides of that carbon. But in this one, there's going to be a different kind of pull because obviously chlorine has a different electronegativity and electron affinity than hydrogen, okay? All right, enthalpies of reaction. Yet another way to estimate the delta H for reactions is to compare the bond enthalpies of the bonds broken to the bonds formed. So again, I've got another diagram here, enthalpy going this way, energy, okay? And we've got, you know, here we've got CH4, this is CH4, and we've got chlorine, all right? And up here, we're breaking off, we're breaking off a hydrogen, and we're separating some chlorine. So how much energy does that take, and how much energy does it take here? Here you'll notice delta H is greater than 0, which means it's positive, which means this reaction is endothermic. Okay? This one is delta H is less than 0, so it is exothermic, okay, for your final reaction. Okay, in other words, there's a crazy equation on there that you can't see. Your heat of reaction is the sum of the bond enthalpies broken minus, this should say right here, your bond enthalpies formed. Okay? Check your book out for the actual equation there if you want to see it written out nicer than what I did. Okay, and then this is a bond enthalpy and bond length table, okay? So when we are talking about bonds, take a look at this. You've got 3 carbon-carbon bonds right here, okay? A single, a double, and a triple. Notice that the length of the single is longer than the length of the double and the length of the triple. So length increases, okay? Length increases with fewer bonds. You'll notice that with all of them. The carbon to nitrogen, the carbon to oxygen, the nitrogen to nitrogen, the nitrogen to oxygen, the oxygen to oxygen. The more bonds you have between something, the closer it is held together, the more tightly it is held, okay? So think of it like a rubber band, a loose rubber band if it only has one loop, like this. But if you double up that loop by making a figure 8, right, and you cross it over and you've got 2, that's going to make it stronger. If you can cross it over